So hello everyone, welcome to the channel. So in this video I'm gonna show you estimate the biomass carbon density prediction using NASA ORNL and MODIS dataset by machine learning approach in Google Earth Engine. So now let's get started. So we're gonna predict the biomass carbon density prediction using NASA's data, NASA and MODIS dataset in Google Earth Engine. So let me explain about what is a biomass is. So biomass refers to organic material that comes from plants and animals, and it is a renewable source of energy. It includes a material such as wood, agricultural crops, algae, waste from the forest, and organic components of municipal and industrial waste. The biomass can be used directly for heating or power generation or converted into a biofuel or a biogas. This form of energy is a part of a carbon cycle as it releases carbon dioxide which is then reabsorbed by the plants during the photosynthesis, making it more sustainable energy source compared to the fossil fuels. The biomass energy helps reduce the reliance on fossil fuels and contributes to the waste management by utilizing the organic waste material. So what is the biomass carbon? So biomass carbon refers to the carbon stored in the organic materials that makes up the biomass, such as plants, trees, and agricultural crops. This carbon is originally captured from atmosphere through the process of photosynthesis. So to predict the biomass carbon density, specifically we are using this above ground mass dataset. It uses we are using various remote sensing dataset including the MODIS vegetation indices, the leaf area index, fraction of photosynthetically active radiation, the land cover types, the digital elevation model, and we are using the specific algorithm, random forest algorithm, to predict the future biomass for the specific region of interest. So we are using this following dataset in order to predict the biomass carbon density for the specific region of interest. So we are using this dataset, NASA biomass carbon density data. This dataset provides an estimate of biomass carbon density, specifically the above ground mass. It is used as a dependent variable for training the model. And MODIS vegetation indices. So it is a normalized difference vegetation index and enhanced vegetation index used to indicate the health and density of vegetation. And next is the MODIS leaf area index and measures the leaf area related to the ground area, and FPAR indicates the fraction of photosynthetically active radiation intercepted by vegetation. And last, we are using this two datasets, that is a MODIS land cover dataset, to provide information about the land cover types such as forest, grassland, or the urban areas. And last, we are using digital elevation model. So the elevation data is included to account for the effect of topography on biomass distribution. So now let me get back to my Earth Engine here. So first we have to define a region of interest for the study area. So we have specifically selected this particular sector. So that is, we are selecting this particular study area, that is Arunachal Pradesh in India. You can able to see that. So this is my study area. You can able to see that. So these here, to define our study area or the region of interest, we define this variable called ROI, that is ROI coordinates. So we use its latitude and longitude of the study area, and you can able to see this latitude and longitude. So now to create a polygon out of this coordinates, we are using this variable called ROI geometry equals to geometry.polygon, and referring to this particular variable containing the latitude and longitude of this particular study area. And next we define map.center object ROI geometry. ROI refers to our study area and refers to the zoom level of 6 here. And next, to add this layer, we define map.add layer ROI with the default visualization parameter. So you can able to see here. Let me turn this on. I'm gonna turn this off. So this is the default visualization parameter, the default color for the study area, and we output the layer as study area. So next we're gonna load our biomass carbon density dataset and select the above ground mass band and convert it into integer. And so now let me explain about this particular dataset. So this is above global above ground and below ground biomass carbon density. So it is a description about this specific dataset. So this dataset provides temporally consistent and harmonized global map of above ground and below ground biomass carbon density for the year 2010 at 300-meter resolution. So you can able to check from the data availability. So data is available from 2010 January 1, 2010 December 31st. So these are the data provider. So you can use this code to access this particular dataset. So now let us move on to the band section here. So we have so here you can able to see we have 4 different bands here. So it's the AGB and AGB uncertainty and BGB and BGB uncertainty. So let me explain about the AGB and BGB here. So above ground biomass carbon, this band provides an estimate of the carbon stored in the above ground part of the vegetation, such as the stems, branches and leaves. It is crucial for assessing the carbon sequestration potential of different vegetation types. And the second band is the below ground biomass carbon, BGB. This band estimates the carbon stored in the below ground part of the vegetation, primarily the roots. The below ground biomass is significant for understanding the total carbon storage in the ecosystem, particularly in forest and grassland. So now let me get back to Earth Engine. So to access this particular dataset, we define this variable called AGB dataset. So to access this particular dataset, we define the variable called AGB dataset equals to image collection NASA ORNL biomass carbon density version 1. So this is the code to access this particular dataset. So in that we're going to specifically select this particular band called .select AGB. So the AGB here refers to this particular band here, that is above ground living biomass carbon stock density. So this we're going to select this particular band called above ground biomass. So we are selected with this that particular band, and next we are mentioning .first function in order to select the first image of this image collection, and to convert to it to an integer. So we define .toInteger function. So next, to visualize the details about this particular dataset, we have mentioned print AGB dataset. So you're going to click this option called run here. So you can able to visualize in the console section. We have this image collection. We have this image. So we're going to click this arrow here. So you can able to visualize this particular band called AGB band, which is signed in 32 with we have mentioned it has mentioned it's the coordinate reference system and the data type as well as the dimensions. So next we have to define the time period for our analysis. So we have to select the time period for this analysis. So for that we defined this particular variable called start year equals to 2010, and similarly we have to define the end time. So I have defined this end year equals to 2011. So the analysis will be performed within the year from 2010 to 2011. So next, basically we have to predict the biomass carbon density prediction for 2020. So for that we have to use some this particular datasets, that is the predictor datasets. For example, the MODIS NDVI and EVI datasets, which can be used to predict the biomass carbon density. So for that we're gonna use this MODIS NDVI and EVI dataset. So for that we define this particular variable called vegetation indices equals to image collection MODIS 061 mode 13Q1. So now let me explain about this particular dataset. So this is the dataset. So the dataset availability is from 2000 to 2024. The dataset provider is USGS EROS Center. So this particular code can be used to access this particular dataset. The resolution of this dataset is around 250 meters. And here you can able to visualize we have two different bands in this particular dataset, that is NDVI and EVI. NDVI refers to the normalized difference vegetation index, and EVI refers to enhanced vegetation index. So with the minimum values and maximum values given here. So the details about this particular datasets given here. The global coverage and the spatial resolution is 250 meters, and the dataset is updated on 16-day basis, and the dataset availability is from 2000 to present. So the bands includes NDVI. The index is used to measure the vegetation greenness and it is calculated using the red and near infrared bands of MODIS sensor. The NDVI value ranges from -1 to +1, with the higher values indicating more dense and healthy vegetation. And similarly, the EVI value, the enhanced vegetation index, the EVI is designed to optimize the vegetation signal with improved sensitivity in high biomass region and better correction of atmospheric and canopy background noise compared to NDVI. It ranges from -1 to +1, similar to NDVI, but it is more responsive in areas with the dense vegetation. So the units, both NDVI and EVI value or dimensional indices. These datasets are scaled by a factor of 10,000, which means the user needs to divide the raw value by 10,000 to interpret them correctly. The 8,000 corresponds to the NDVI or EVI value of 0.8. So let me get back to the Earth Engine here. So to access this particular dataset, we are using a variable called vegetation index equals to image collection MODIS 06 mode 13 Q1. So to access this data, we are using the specific code, and in that we are selecting the two bands dot select NDVI band, and we are selecting the EVI band. So we're going to filter with the specific filter date, that is filter date from start year and end year. So we have mentioned the start and end year, that is 2010 and 2021. So this particular dataset is available from 2000 to present. And next we're going to filter with the specific month. So for that we define dot filter dot calendar range. We are selecting specifically in the year, the month, 5th month and the 9th month of the year. So once you've selected your month of your choice here, so next we have to apply the scaling factor. So to apply scaling factor, first we have to define a loop structure. So to define a loop structure, we define the dot map function image. So basically we're applying this scale factor to both the NDVI and EVI bands here. And next we have to return the image. So return image dot multiplying the scale factors. And so next we want to have the properties of the input images for the output, specifically for the system time start and the system time end. So for that we define dot copy properties image dot property names. And so once the scaling factor is added, so we can get a mean image. So we can get an average image once we apply the scaling factor. So to obtain an average image, we define this particular function dot median function. So we are applying a median function specifically because the MODIS NDVI and EVI has a lot of image collection for the specific timeline for 2020 to 2010 to 2011. So in case of this particular dataset, that is our above ground biomass dataset, this particular dataset is available only for 2010. So to predict the biomass carbon density, so we are using this predictor datasets, that is our MODIS NDVI and EVI dataset. So in order to apply this to predict the biomass density, we have to obtain average image to predict the biomass carbon density. So using 2010 biomass carbon density dataset, we're going to predict the 2020 biomass carbon density using this predictor datasets, predictor datas like NDVI, MODIS NDVI and EVI datasets. So for that we are applying the specific function to get an average image out of this particular year from 2010 to 2021. So for that we are applying this function called dot median function. So next to visualize the details of the specific image, we defined print. So we're going to mention this particular variable name here, that is vegetation indices. I'm going to copy this and I'm going to paste it here. And now we're going to run this code again. So here in the console section, we have two bands. So the one band which represents the NDVI and the second band which represents the EVI. So next we're going to add this NDVI and EVI layer to the map clip to our region of interest. So for that we defined map.add layer vegetation indices referring to this particular variable, and .clip ROI geometry referring to a region of interest with the default visualization parameter and output the layer name as vegetation indices. So once you run this code, we can navigate to the layer section here. So you can able to visualize this particular layer here, that is vegetation indices. I'm gonna click this. So now you can able to visualize the layer here. So we're gonna click this option and click this option called the setting option, and here you can able to see we have we're gonna select this one band. So we have two different bands here. One band represents NDVI and the second band which represents the EVI band. So now we're gonna select NDVI and let us increase the contrast of this image. We're gonna click the stretch 90% and we're gonna click apply. So now here you can able to visualize the result here. So this is the NDVI image of this particular study region. And similarly, suppose if you want to see this second band, that is EVI, enhanced vegetation index, we can click this band here. And similarly, we're going to apply the stretch 90% and we're going to click apply. So now this is the EVI band, which is completely cloud free. Both the NDVI and EVI band is completely cloud free, which is suitable for our analysis. So now let me close this. So let us follow up this code here. So next, so the other data set that is very helpful in this study, that is the MODIS LAI and FPAR dataset. So let me I will show that dataset here. So this is the dataset availability. So the dataset is available from 2000 to 2024. So these are the bands that is available in this particular dataset. So you can able to see there is around 6 different bands available. So we're gonna select these 2 bands. So first band, which represents FPAR 500 meter resolution, the fraction of photosynthetically active radiation. So the minimum and maximum values given, the scale factors are given here, and similarly the LAI, that is 500 meter resolution, which has the description is the leaf area index, the scale factors, and the minimum and maximum value. So let me explain about this particular dataset. So the spatial resolution of this particular dataset is around 500 meters, and the temporal coverage, the dataset is updated on 8-day basis, which allows for the near real time monitoring vegetation changes and dynamics. The data is available from 2000 to present. So the data bands we are using is LAI, that is leaf area index. So LAI measures the total area, total leaf area per unit ground area, and it is critical parameter for understanding the amount of leaf material in a given area. It ranges from 0 to 10, where the higher value indicates the denser foliage. And FPAR, the fraction of photosynthetically active radiation. The FPAR measures the fraction of incoming solar radiation in the photosynthetically active wavelength from 400 to 700 nanometers that is observed by the vegetation. It ranges from 0 to 1, with the value closer to 1 indicating more radiation being absorbed for the photosynthesis. So the unit for this particular band is LAI is a unitless, but is typically represented as meter square leaf area per meter square ground area. The FPAR is a fraction and also unitless, representing the portion of available radiation absorbed by the canopy. So let me get back to the Earth engine here. So to access this particular dataset, we are using a variable called LAI and FPAR dataset equals to image collection MODIS 061 MODIS 15A2H. So this particular code I can able to access this dataset here. So in that we're gonna select these 2 bands that is available in this dataset. So we're gonna to select that, we can mention .select LAI. So to select this band from this dataset, we are using .select LAI 500 meters and FPAR 500 meters. And next we're gonna filter with the specific start year and the end year. We have already mentioned as the start year is 2010 and the end year is around 2011. So you can able to see here the start year and end year. So next we're gonna filter with a specific month here. So for that we define .filter calendar range 5 and the 5th month and 9th month of this year. And so next we have to apply the scaling factor to this LAI and FPAR dataset, so FPAR band. So first we have to create a loop structure, and to in that we're going to create a function. So for that we define .map function image, and we're gonna create a variable called LAI equals to image.select LAI 500 meter dot multiply 0.1. So let me show you that dataset here. So I can able to see the scaling factor for this FPAR and LAI. So LAI has a scaling factor of 0.1 and the FPAR has a scaling factor of 0.01 is a scaling factor. So let me get back to the Earth Engine. So here to apply the scaling factor, we define image.select LAI 500 meter. This is the band dot multiply. The scaling factor is 0.1. And similarly for the FPAR, we have defined this variable called FPAR equals to image.select FPAR 500 meter resolution. This is the band name. And to apply the scaling factor, we define dot multiply 0.01. And to return this particular so once you apply the scaling factor, we're going to return the LAI first here, and next followed by we have the FPAR. So one thing just to remember, so to copy the input properties for the output as specifically for the system start at time and the system start end, which is also included in the properties. So for that we define dot copy properties image dot property names. And next to obtain an average image for the specific dataset, that is for MODIS LAI and FPAR dataset for the year 2010 to 2011. So to obtain a single an average image out of for the specific timeline, so we define this function called dot median function. So next suppose you want to visualize the details of this image, you can just use this print and mention the variable name LAI FPAR dataset. So to visualize the dataset, and now to add this layer, we define the map.add layer LAI FPAR dataset dot clip ROI geometry refers to a region of interest with the default visualization parameter, and output the layer name as LAI and FPAR. So now once you did that, we can navigate to this option called run and click this option called run. So now in the layer sections, we're gonna click this band called LAI FPAR. You can able to see that. I'm gonna click this. So now we can currently visualizing the LAI and FPAR dataset, the averaged LAI and FPAR dataset for the year 2000 is ready. So now in the layers section, I'm gonna click this option here. So let me drag this down here. Select the single band. And here we're gonna select the custom option here, and in that we're gonna increase the contrast by 90%, and we're gonna click apply. So the LAI shows the density of the vegetation cover much better, so much better than the NDVI and EVI, because it is not saturated with vegetation cover. So next we're gonna select the second band, that is FPAR. So the FPAR, which represents a fraction of photosynthetically active radiation. So the FPAR measures the fraction of the incoming solar radiation in the photosynthetically active wavelengths, and it is absorbed by the vegetation. So the value is closer to 1, indicating more radiation being absorbed for the photosynthesis. So once you selected the contrast to the stretch type of 90, I'm going to click apply. So now here you can able to visualize the result here. So let me turn my study area off here, so you can able to see now clearly. So now let me close this. So the next step I'm gonna call the land use land cover data of MODIS dataset. So I can able to see that. So to load the MODIS land cover dataset and select the land cover type bands. So to access the land cover dataset, we have defined this variable called land cover equals to image collection MODIS 061 MCD12Q1. So let me show you this. So this is the MODIS land cover data type here. So using this specific code, you can able to access this particular dataset. So the data availability from 2001 to 2022. So these are the bands that is available in this particular MODIS land cover data set here. So you can able to see the different bands that is available for this particular MODIS land cover dataset. The LC type 1, so which represents the land cover type 1 annual international biosphere program IGBP classification. So you can for the specific band here, these are the following classes that is available for LC type 1 class table. Starting from these are the different land covers that is available for this LC type 1, and similarly the LC type 2. These are the following land cover classes that is available, and similarly you can able to see the different classes LC types that is available here. And we are specifically using the land cover data type data set because it helps us to differentiate the croplands, the farmland and the bare land, and the urban areas with the forest areas. It is very helpful. So basically this particular data set is very helpful in differentiating the different land cover types. For example, farmland, bare land, and also to differentiate the urban lands from the forest types. So for that this particular dataset is very helpful. So for that we define the variable called land cover equals to image collection MODIS 061 MCD12Q1, and in that we are specifically selecting this particular land cover type, that is this particular band LC type 1. So the LC type 1 which represents, this is the LC type 1 band here. So these are the following land cover classes that is available in this LC type 1 band, starting from evergreen to water bodies and bare and permanent snow and ice, cropland and natural vegetation, and mosaics, urban and built-up plants, croplands. So you can able to see these are the different color which indicates the different land cover types in this particular band of LC type 1. So next we are using .mode function. So you are using this specifically this function mode function because the mode function which is used to so basically it is used to get the most frequent classes, the most frequent land cover classes over the last 2 decades, because I want to make a single land cover map only which shows a different land cover types, specifically to show the forest, farmlands, and etc. And so now we have our land cover dataset is also ready. So next we're gonna load our digital elevation dataset into Earth Engine. So for that we define the variable called elevation equals to terrain product image USGS GTOPO30, and in that particular dataset we're gonna select this particular band called elevation. So let me show you that dataset here. So this is the global 30 arc second elevation. So dataset availability is from 1996 to 1996. So dataset provider is your United States of Geological Survey. So we are using this specifically this particular dataset. So in order to visualize the terrain details of this particular study area, so for that we are using this particular dataset. So to add this layer, we define map.add layer elevation.clip based on the study area with the default visualization parameter, and output the layer lane as a dem. So now we're going to visualize it. So navigate to the layer section in that, and we're going to click this dem. So now you can able to visualize the dem of this particular study area. I'm going to turn this off. So now we can able to visualize the terrain details of this study area. You can able to see that. So now we need to combine all the datasets. That is all the predictor datasets. So like the AGB, that is the biomass data, and other data like NDVI, EVI, LAI, and the FPAR and the land cover dataset into a single image. So these are the datasets which act as a predictor in our modeling. So to predict our biomass carbon density prediction for 2020. So now I need to make it to a single image. So basically we're going to create a single image stack layer for our biomass carbon prediction for the year 2020. So these are the predictor datasets. So to combine all the dataset together, we define the variable called combined dataset equals to image.cat. So we are using specifically this cat function is to combine all the datasets together. So first I'm gonna use this biomass data, that is AGB, the above ground biomass dataset. So we defined as AGB dataset here, and followed by the vegetation indices. The vegetation indices that includes the NDVI and EVI, that is normalized difference vegetation index and enhanced vegetation index, followed by LAI and FPAR dataset. So the LAI which represents the leaf area index, and FPAR which represents the fraction of photosynthetically active radiation dataset, and at last the land cover data. So now to visualize the details of this dataset, we're gonna mention as print, and I'm gonna mention the variable name here, that is combined dataset. I'm gonna copy this and paste it here, and I'm gonna run this code here. I'm gonna click run. So in the console section, you can able to see here, that is our so you can able to see here the image NASA ORNL biomass carbon density. I'm gonna click this arrow here, and now here in the bands we have 6 elements here. I'm gonna click this arrow here. So now currently you can able to see the bands here. So we have the AGB, that is biomass, above ground biomass, and NDVI, EVI, LAI 500 meter, FSPAR, and the land cover type. So we have managed to combine all the datasets together into a single image. So the next step is to create a training dataset by sampling the combined image within the ROI. So to create a training dataset, we defined a variable called training data equals to the combined datasets, refer to this particular variable here, dot stratified sample. So we want to create a training dataset for the prediction model. So for that we define this variable training data equals to combined dataset dot stratified sample, and the num points here refers to, so the num points here which refers to the number of points. So it means that how many number of points you need to have for per pixels. So for example, I would like to have 100 samples per pixel for each of the unique biomass value we want to have is 100 samples, and the class band which refers to the AGB, that is our above ground biomass, and last the region which represents our study area, that is our region of interest, which is indicated by ROI geometry, and last the spatial resolution. So we have given the spatial resolution to be around 500 meters. So next we are to train a random forest model using the training data. So to train your model using your training data, first we have to define a variable called random forest model. So we are going to use this particular model called random forest model to we defined a variable called random forest model equals to classify.smile random forest 80.train. So they are different types of classifiers that is available in Google Earth Engine, but we need to select only those particular classifiers that can be used for in the regression format. For example, currently we are using this smile random forest model as a classifier, or you can use the other classifiers like a smile gradient tree boost, or the KNN smile KNN, or the smile nave base, and or the smile random forest. So they will have no problem for the regression format. It is true they have the classifier, but we can convert them to the regression format. So for example, we are going to use this smile random forest classifier. So we have mentioned as 80% dot train here. So the features will be our training data have mentioned here, so you can able to see that. So the 80% of the training samples will be used for this model here. So the features referring to the training data, referring to this particular data set. And next the class property, this refers to our AGB, that is the above ground biomass. And the input properties we have mentioned as the combined dataset. So the combined dataset, which refers to all the datasets, you can able to see from this variable here, which refers to contain all the other datasets we have shown earlier here. So this particular variable has a combined dataset here, which refers in the input properties as a combined dataset dot band names. So these are the properties that we want to train our model based on the biomass imagery that we have. But this current line of code which represents still it is a classifier, So to convert to a regression format, we define .set output mode. So for that we define set output mode regression. So now we have converted it to a regression format. So now the model is ready to go. So now the model is ready. I want to apply the model on the properties. So the next we have to define the predictors by removing the AGB band from our dataset, from the dataset here. So the AGB refers to the above ground biomass. So we define this variable called predictors equals to the combined datasets. So referring to the combined datasets of all the LULC and NDVI and EVI bands. So I'm going to refer this variable combined dataset dot band names, referring to the band names in this particular variable called combined dataset. And in that we're going to remove the AGB band here. So basically to predict the biomass carbon density for 2020. So this particular dataset is just a source data. So to predict that, first we have to remove this band from our combined dataset. So for that we define this variable called predictors equals to the combined dataset dot band names and dot remove AGB. So that refers to above ground biomass. So reason for removing this particular band is this band is a source band, that is a data source. So it's not a predictor. So we're gonna use the other set of data sets using that, like the MODIS land cover and NDVI, EVI and LAI to predict the biomass biomass carbon density for 2020. So for that we're gonna remove this particular band, AGB band. So now applying the trained model to predict the above ground biomass and rename the output bands. So to apply the trained model to predict the above ground biomass, so we define this variable called AGB prediction. So basically we are using the random forest model to predict the 2020. We are using 2010 biomass data to using that, and with the predictor data sets like LULC, NDVI and EVI and LAI datasets to used as a predictor datasets to make a prediction for the 2020 biomass, that is biomass carbon density in 2020. So for that we define this variable called AGB prediction, that is above ground biomass prediction equals to the combined dataset. So the stacked dataset we have set it earlier, and in that we're gonna select predictors referring to this variable containing all the datasets except the AGB band, and dot classify, we are applying the random forest model, and we're gonna rename this particular as a predicted AGB as the output layer. We are renamed as a predicted AGB. So next to add this layer into Earth Engine, that is to add the original and predicted above ground biomass layer to the Earth Engine. So we define map.add layer combined dataset dot select AGB dot clip ROI, that is our region of interest, with the default visualization parameter, and output the layer name as original AGB, that is above ground biomass. And similarly we're going to add the other layers, that is the predicted dataset, the predicted AGB. So for that we define map.add layer AGB prediction dot clip. The ROI geometry refers to study area with the default visualization parameter, and the output as a predicted AGB. So once you did that, we're going to run this code here. We're going to click run here. So here you can able to visualize the layers here. Let me turn off this layer. So we have this layer called original AGB, that is above ground biomass, and this is the predicted AGB, that is predicted above ground biomass. So you can able to see that. So now let me navigate to the original AGB. In that we're going to click this option, and in that we're going to select the custom options. We're going to select the contrast to be around 90%, and once you did that, we're going to apply this value here. So now you can able to visualize the result here. So you can able to see from the range here, the value varies from 10.70 to 96.3. So as I said earlier, this particular image is a high quality image which has a spatial resolution of around 300 meters. But this particular image is available only for one particular year, that is for the 2010. So this particular the above ground biomass, this dataset is available only for one particular year, that is 2010. So this dataset is not available in a multi-temporal format, and I cannot have the for the spatial temporal ranges, like I cannot have for 2009 or the 2020. So or the other set of years, because this dataset is only available for the year 2010. So but I was using this dataset, I have used this the random forest model. I have used this model to simulate the biomass for the year. So using this random forest model, you can feed this this biomass data of 2010 into this random forest model, and you can predict the future possible trend of this biomass for 2015 or 2020 using this random forest model I have shown you earlier. So this models could be very useful in order to predict the future the biomass carbon density for the year 15, 20, like that. So similarly, let us take a look at the predicted AGB, that is above ground biomass. Gonna turn this on here. So we're gonna click this option here, and gonna adjust the contrast to 90%, and so now you can able to visualize it. I'm gonna apply. So now this is a predicted AGB. So you can able to see from this predicted above ground biomass here, the value starts from 17.54 to 138.55. So it is kind of close here, or let me show you that here. I'm going to close this. So I'm going to navigate to the original AGB. Let me click this option here. So the values here varies from around 10.7 to 96.3. But in the predicted, it is around 17.7, 17.6 to 138.3. So it is kind of close, which you can able to see from here. So I'm going to close this, and let me show you here. I'm going to adjust the transparency here. So you can able to see the image here. So I'm going to turn this off here. I'm going to turn this off. This is the original versus the predicted. So you can able to see that the original versus predicted above ground biomass. So you can able to see that. So here, and also you can check this predicted versus original value using this option, that is inspector tool here. So I have clicked the inspector tool. I'm gonna click the value here. So now we can able to see from this image here. So we have this predicted versus the original value. So the predicted value, the original is around 90, is value around AGB is around 90, but the predicted is around 91, which is close. Let me reduce these things. So I'm gonna let me minimize these. So I'm gonna only open this one. So you can able to see the AGB value. So similarly, I'm gonna click the value and check in other areas. So I can able to see the values here. In predicted, AGB is around 17.35 in the predicted, but in the original it is around 22.28. And similarly, I'm gonna click here. So let me show you here. So you can able to see the value here. The predicted is around 125. And the original value is around 146. It is kind of almost close to it, and I'm gonna click here, and we're gonna see the value here, the predicted above ground biomass versus the original above ground biomass. So the original is around 54, the predicted is around 60. So it is, you can able to see that it is kind of very close to towards the predicted is kind of close to the original AGB value here. So I have using the inspector tool, you can able to see that. So next we're gonna analyze the accuracy between the original and the predicted AGB, that is above ground biomass. So we're gonna using a Pearson correlation method for that. So we're gonna analyze the accuracy between the predicted and original using the Pearson correlation method. So to calculate a Pearson correlation between predicted and original AGB. So for that we define this variable called correlation equals to. So to calculate the correlation, we define a variable correlation equals to AGB prediction, referring to our prediction data set here in predicted image, and dot add bands, they're referring to our combined data set containing all the EVI, NDVI, LULCs and other data sets. And in that we're going to select AGB. So we are selecting AGB because we have removed it from the combined data set. So now we are selecting AGB dot reduced region. So dot reduced region. So using reduced region function, we can able to calculate the correlation between the predicted and original AGB. So the reducer, we are referring to reducer reducer dot Pearson correlation function, and the geometry referring to the study area, and the spatial resolution. And we set the spatial resolution to be around 10,000 because it contains a lot of pixel values here. So in order to reduce that, we have mentioned as 10,000 as a spatial resolution for our correlation analysis. So now let me navigate to the console section here. So now to visualize the result, I'm gonna enter as print, and we're going to see the details of this correlation. I'm gonna take this variable here and I'm gonna paste it here, and we're gonna run this code. Click this option called run. So we're gonna visualize the result here in the objects. You can able to see in the console section here. I'm gonna click this down arrow button. So here the correlation is around 0.85, and the correlation value is given here is around 85.10% of biomass changes is correct. So between the predicted and original above ground biomass value. So now we have performed our correlation analysis. You can able to see here, which is around 85% shows here the correlation between the original and AGB and the predicted AGB1. So similarly in the inspector tool, you can also see here the difference between the original and predicted value here. So it is around 75 for in the original AGB value. The predicted is found to be around 71.75, which is kind of close here. And similarly, you're going to try in other areas here. So you can able to see here the original and the predicted here. So the original AGB value is around 65. So let me show you the units for this. So the unit for this particular unit, that is above ground biomass, so which is represented as mgc/hectare. So that is a megagram of carbon per hectare. So unit for this particular data set is megagram of carbon per hectare. So you can able to see the difference between the original and predicted value, and similarly in this part of the areas. So here you can able to see here the original AGB value is around 51 megagram of carbon per hectare, which is when the original is found to be around 51, and in the predicted is found to be around 58. So it is kind of close to each other. So now next we're gonna perform we're gonna calculate the R squared value from the Pearson correlation. So we're gonna calculate the R squared value to assess the correlation from the Pearson correlation to assess between the original AGB and the predicted AGB. So to do that, we defined a variable called R squared equals to. So we define the variable called R squared equals to number correlation dot values dot get. So the get function usually extract all the values from the dictionary. So for that we are using this get function. So the 0 here, which extract the first value from the list here. So for that we have mentioned as 0. And at last we had included dot power to the power of 2 which is indicated, that is R squared value. So let me explain about this particular thing. So what is R squared value? So R squared value is a statistical measure that indicates the proportional variance in the dependent variable that is predictable from the independent variable. So it is derived by squaring the Pearson correlation coefficient R, which measures the strength and the direction of all linear relationship between the two variables. So R squared value ranges from 0 to 1. So value 1 indicates the model perfectly predicts the data, meaning all the variability in the observed data is explained by the model. A value 0 indicates the model does not explains any variability in the observed data. So let me get back to the Earth engine. So now next to print the Pearson correlation coefficient and the R squared value, so we defined a print correlation dot values dot get 0. So we are referring to this set of thing here, and to get the R squared value we defined a print R squared referring to this particular variable. So to get the R squared value we are referring to this for all the thing here, with we added this power to the power of 2 here. So now to visualize this thing, we navigate to the console section here. So you can able to see this is the correlation value between the original and predicted AGB, and this is the R square value between the original and predicted one, which is around 72% R square value, and the correlation value is around 85%, which indicates here between the original and predicted AGB. So next, the prediction for the year 2020. So we have to to do the prediction of biomass density for the year 2020 using the 2010 data here. So for that, so we have to perform prediction for the year. We have to perform the biomass carbon density prediction for the year 2020. Certainly, this model may have a overestimation or underestimation. So because the model has its own uncertainty. So now to do the prediction for the biomass carbon density, above ground biomass carbon density for the year 2020, first we have to load and pre-process the NDVI and EVI data of MODIS dataset here. So we have to define a variable called vegetation indices 2020 equals to image collection MODIS 061 MODIS 13Q1 referring to that dataset here. And in that we have selected as previously has performed this. So similarly we're going to perform this. So we're going to select NDVI and EVI band, and we're going to filter the date for 2020 and 2021. Previously we have filtered the date for 2010 and 2011. So now we are doing the prediction. So we are selecting the filter date for 2020 and 2021. And next we're going to filter for the specific calendar range. So for that we are using a dot filter, calendar range, referring to the month 5 and 9th month of the year. And to create a loop function, to loop structure, we are using dot map function and image, and we're going to return the image and multiply with the scaling factor. So we are using this is a scaling factor for this MODIS dataset for NDVI and EVI band. So this is a scaling factor, and similarly we are copy properties of the image, and to get a median, that is an average image for the NDVI and EVI value for the year 2020 and 2021, we define dot median function. And similarly we are using LAI and FPAR data for 2020 for the prediction of above ground biomass density for the year 2020. So we are using similarly variable LAI and FPAR 2020 equals to image collection MODIS 061 MODIS 1582H, and in that we're going to select LAI 500 meters and FPAR 500 meter bands here from this dataset, and we're going to filter it for this timeline of 2020 and 2021, and with specifically filtering the calendar range between the 5th month and 9th month of the year. And again we're going to create a loop function, loop structure for this, and we define map function image, and we are referring to that creating a variable LAI, and in that we are selecting this particular band, and we are applying the scaling factor for this data set here. So you can able to see that, and again for this FPAR we are selecting the image, in that we're going to select this particular band and multiplying with the scaling factor of 0.01, and we're going to return, and we're going to add this return first this LAI band, and we're going to add this FPAR band, and similarly the copy properties, and to get an average image out of this particular MODIS dataset for the LAI and FPAR get an average year for this year 2020 and 2021, we define this function dot median function. At last, we have to combine all this data together to give to find the prediction value for this above ground biomass. So for that, we defined a variable called combined dataset 2020 equals to image cat function. So we are here referring to vegetation indices containing NDVI and EVI value, and similarly we are referring to the LI and FPAR dataset of MODIS. We are referring this variable, and the land cover data of MODIS. And next, to perform the prediction, so similarly we are using this particular model called random forest model. So to prediction for the above ground biomass for the 2020 using our trained model, that is our random forest model, we define the variable called AGB prediction 2020 equals to the combined dataset 2020, referring to this particular variable variable called variable combined dataset 2020, referring to this particular dataset here. So to refer or to combine all this dataset together, we define image.cat, referring to this NDVI and EVI value, and LAI and FPAR dataset and land cover dataset. So to perform the prediction for 2020, we are using our random forest model. So define the variable called AGB prediction 2020 equals to combined dataset 2020, referring to the stacked layer of this datasets, and in that we dot classify random forest model and rename as AGB 2020. So once you did that, we have to add this layer in Earth Engine to visualize the result of our predicted AGB value for 2020. So for that, we defined the map.add layer AGB prediction 2020 dot clip. ROI geometry refers to region of interest, and this refers to default visualization parameter, and output the layer as AGB 2020. So once you did that, we're gonna run this code. We're gonna navigate to the run section and click run here. So we're gonna visualize the result here. So navigate to the layer section here. We're gonna turn on the original predicted and AGB value here. Similarly, I'm gonna make sure that I'm gonna increase the contrast to 90%, and we're gonna apply it. So now you can able to see the original and the predicted one here, and I'm gonna turn on the AGB for 2020, the predicted one here for 2020 here. I'm gonna click this option here, and in that I'm gonna navigate to this option on the custom section. I'm gonna click 90% stretch here, and it's loading here, and click apply. So now this is the AGB 2020, that is above ground biomass of 2020. You can currently visualizing the image here, and this is the original image for 2010, and this is the AGB, that is above ground biomass for 2020. You can able to see that here. So now here you can able to see that we are currently visualizing the this is the original above ground biomass, and this is the predicted above ground biomass here. So it's loading here. We're gonna wait for some time, and this is the above ground biomass for 2020 we have performed using the random forest model as a machine learning approach. We have used it for it to predict the above ground biomass for the year 2020 using this the random forest model here. So in this video I have shown you how to predict the biomass carbon density using the NASA and MODIS dataset by a random forest model using machine learning approach in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and like us. So thanks for watching.